The next unit that we'll be starting to study is called stoichiometry. Stoichiometry involves a set of calculations that you can do to determine how much of your reactants should go into an equation and how much of your products you can expect to get. Before we begin to write things down, we have just a couple of comparisons to make. I often compare stoichiometry to something like a recipe for making some food. Maybe you're going to bake something, or maybe you're making something as simple as a s'more. If you're going to make a s'more, you need certain amounts of different things. Usually you use 2 graham crackers, 3 squares of chocolate, and 1 marshmallow. This is your recipe. This would be like telling you how many of each reactant do you need. So here's a couple of example questions. Think about this to yourself. How many graham crackers do you need to make 3 s'mores? Hopefully you said 6. How many do you need to make 5 s'mores? Hopefully you said 10. You can use your recipe as a ratio of ingredients to decide how much you need to put in based on how many you want to make. Here's a couple more. How many marshmallows do you need to make 3 s'mores? Hopefully 3. And 5? 5. This one might be a little harder. How many whole s'mores can you make with 8 squares of chocolate? Only 2. And then you end up with some pieces left over. You were limited in how many s'mores you could make because you ran out of chocolate. Recipes for chemical reactions are very much the same, at least in idea. They tell you how much of your ingredients or your reactants should go in and how much of your products you can expect to get. They also might tell you if there's anything left over or if there's anything that ran out. So stoichiometry, and here's where we start to write things down, is a set of calculations involving balanced chemical equations. So we're going to use all of those skills that we've been leading up to, writing formulas, writing equations, balancing equations, and we're going a little bit further with those skills. For example, pretty simple equation, H2O, or water as a liquid, can be broken down into hydrogen gas and oxygen gas. We know that each of those has to have a 2 because they are both diatomic elements. But if you look at this equation the way it's written, it's very much like a recipe with no amounts. We don't know how much water to use. We don't know how much hydrogen or oxygen we'll get. How useful is that recipe? Imagine going to bake brownies or cookies, and you read the recipe and it says flour, sugar, eggs, vanilla, and baking soda. And you think, that's not very helpful. That doesn't tell me any of the amounts that I need to put in. It doesn't tell me how many cookies or brownies I can expect to get. This equation, right now, is a recipe with no amounts. To fix that, we have to balance the equation. How many hydrogens do we need? How many oxygens do we need? Balance the equation with a 2, and a 1, and suddenly this equation is much more useful. When it's balanced, it will tell you how much of the reactants and how much of the products, what you can expect, or what you should put in. If it's not balanced, it tells you almost nothing. You don't know anything about how to carry out that reaction or how much of each thing you should use. Once we've taken care of that balancing though, we can use the reaction to get three pieces of information. Just like our ratio of s'mores ingredients, we needed 2 graham crackers for every 3 squares of chocolate and for every 1 marshmallow. Equations, when they're balanced, are also ratios. You can use them to determine how many molecules of each thing you should have. 2 molecules of water will make 2 molecules of hydrogen and 1 molecule of oxygen. So that would be a ratio of molecules of products and reactants. You can also use it as a ratio of moles. Those numbers in front also can represent moles. 2 moles of water produces 2 moles of hydrogen and 1 mole of oxygen. And this is the ratio that we'll be dealing with today, the ratio of moles. And then next week, we'll get to learning about the ratio of mass. We know that mass has to be conserved during chemical reactions, so you can also use this to compare how many grams of water to how many grams of hydrogen to how many grams of oxygen. And if you think about where did these numbers come from? Well, what does 1 mole of water weigh? Add up 2 hydrogens, approximately 1 each, plus oxygen, approximately 16. 2 plus 16 is 18. 18 times 2 is 36. Same thing over here. How much does 1 mole of hydrogen weigh? Approximately 1 times 2 for H2 times 2 in front, and you end up with 4 grams of hydrogen. We could do the same for the oxygen. We'd have 16 times 2 is 32. So eventually next week we'll be dealing with ratios of mass. And those mass ratios come from the mole ratios that we're going to learn today. And remember, as we learned before, when we talked about balancing equations, mass has to be conserved from reactants to products. You can't make mass, you can't destroy mass, at least not in this room. So how do we deal with this ratio of moles? How do we deal with this recipe for our chemical reactions? These are called mole-to-mole problems because you'll be given information in moles and you'll be solving for information in moles. I highly recommend that you use factor label for these questions. It's going to be tempting because these questions are relatively simple when you get to the math. It's going to be tempting just to ignore factor label and do it in your head. I'm warning you that next week will not be this simple, so you need to practice the method with the first ones, and then you'll know what to do a little bit better when we get to the second kind. Okay, so let's start with an equation to balance. Pause the video and balance the equation. Hopefully you ended up with a 3 and everything else is 1s. Here are the first questions we'll solve. How many moles of chlorine are consumed if 1 mole of CS2 reacts? How many moles of CCl4 are formed? Just like all of our other factor label questions, you need to start with what's given in the question. So if we take the first question and look for the number that we're given, 1 mole of CS2, that's what we'll start with. What are we being asked for? How many moles of Cl2? That's what we need to end with. So here's our equation again, balanced just like it was before. Remember with factor label, you always start with your given. Our given was 1 mole of CS2. We're looking for moles of Cl2. This is where we want to end up, moles of Cl2. So how do we get there? Moles of CS2 need to cancel. I need to get rid of them if I want Cl2 in my answer. If moles of CS2 need to cancel, they need to go on the bottom next. And you look at the equation to figure out what number goes with them. What number is in front here if you don't see any? It's a 1. So 1 mole of CS2, and then whatever you're looking for goes in the top spot. 3 moles of Cl2, because that's what we want to find. Moles of CS2 cancel, and we just need to do the math. Sig figs here, 1 based on our given. So of course this is just going to be a whole number. The answer is 3 moles of Cl2. The second question said how many moles of CCl4 would be produced. We have the same piece of given information, so we'll still start with 1 mole of CS2. Again, we need that to cancel, so it will go in the bottom spot next. And this time we're looking for moles of CCl4. Look at your equation. What number's in front of it if you don't see any? It's a 1. So this one is even easier. Check your sig figs. Just have 1 again. So our answer is 1 mole of CCl4. Let's try another one. Same equation. How many moles of S2Cl2 are formed if 6 moles of Cl2 reacts? Here's our equation. Look for what you're given in the question. 6 moles of Cl2. So that's what we start with. Now the moles of Cl2 need to cancel. Those are going to go on the bottom spot. And you look to the equation, what number is in front of it, and it's a 3. So 3 moles of Cl2. What are we looking for? How many moles of S2Cl2? That will go in the top spot. Look to the equation, what number is in front of it if you don't see any? It's a 1. Check your sig figs. Whole numbers again. 6 divided by 3 is 2 moles of S2Cl2. Next question. How many moles of Cl2 react with 3 moles of CS2? Same equation. Start with what's given in the question. 3 moles of CS2. Moles of CS2 need to cancel, so those go on the bottom. Again, we get that number from the equation. This time we're looking for how many moles of Cl2. Cl2 goes on the top. Take the number from the equation. Check your sig figs. Whole numbers again. 3 times 3 is 9. 9 moles of Cl2. It is important at this point that you start labeling your answers with the substance in addition to the unit and your answer with sig figs. If you don't label this as chlorine, I don't know that you've found chlorine necessarily. So you have to start labeling the substance as well as the unit and your number with sig figs. New equation. Pause the video and balance this equation. Hopefully you ended up with a 2, a 1, a 1, and a 2. First question. How many moles of AgNO3 are needed to make 2.5 moles of HNO3? Look for what's given in the question. 2.5 moles of HNO3. So that's what we start with. Moles of HNO3 need to cancel, so those will go on the bottom spot next. Look to the equation for the number. It's a 2. And then we need to decide what are we trying to find. How many moles of AgNO3? AgNO3 is going on the top. Look to the equation for the number, and it's a 2. Notice what happens to these 2's. They cancel. So we really don't even have math to do here. Check your sig figs. This time we have 2. We're going to keep 2. So 2.5 moles of AgNO3. The last label that's right here at the top is always going to be the label that's on your answer. One more question. If a reaction produces 7.7 moles of HNO3, how many moles of Ag₂S are made? Here's your equation. Look for what you're given. 7.7 moles of HNO3, so that's what we start with. Moles of HNO3 need to cancel, so they're going on the bottom. Look to the equation for the number. It's a 2. What are we trying to find? How many moles of Ag₂S? Ag₂S is going on the top. Look to the equation for your number. Check your sig figs. We'll keep 2. And the answer comes out 3.9 moles of Ag₂S. Remember from when we've done sig figs before, the number of moles is an exact number from your equation right up here. These numbers are exact, so we don't look at those for sig figs. You're just going to look at the number you start with. You should be ready to do your homework. We will take care of stamping that on Monday, and next week we'll move on and do some gram problems a little bit later. Have a good weekend.